This is problem 2 of chapter 17 of Giancoli 6th edition. So the question is, how much work does the electric field do in moving a proton from a point where the potential, so let me write the potential here, where the initial potential is plus 125 volts, to a point where the potential is lower, the potential is minus 55 volts. Okay, so certain things to remember here. First thing that we see is the electric field or the electric force is doing this motion, is moving this proton. This is the natural motion of the proton. There is no external force involved here. And we know that the proton always goes from high potential to low potential in this natural process when it's guided by the electric field, by the electric force. We also know that whenever we have this natural motion, the potential energy decreases. So we also know that the work done by this electric force or also by gravitational force will be minus the difference in potential energy. In this case, we are talking about electric potential energy. So this, we get the minus sign here because this is the natural motion of the object, and is the work done by the electric force. If we are thinking about gravitational force, by the gravitational force. So this minus sign is by the electric force, is not by an external force, it's the natural motion of the particle. Very well, so these are two important things to remember. What we want to find is the work. We know that this work will be positive. The direction of the force and the direction of the displacement is the same, and that also explains why we need to put this minus sign. If the work has to be positive, and this difference in potential energy will be negative because the potential energy is decreasing, so that explains why we need to put the minus sign. Okay, so these are all things for us to remember. The question here is simple, it just wants the work. We know that the work is minus, the work done by the electric force is minus the change in potential energy. We know the relationship between potential energy and potential. Remember that the potential is the potential energy divided by Q, right? So we know that the work is equal to minus Q and the change in the potential, right? So I'm using this equation here, and instead of writing now the potential energy, I'm writing the potential, right? So the work, again, let me repeat this over and over, the work done by the electric force, the natural motion of the particle, is controlled by this equation here. Remember that the work done by an external force is different. The work done by an external force is equal to plus Q and the change in potential. Because here, the work done by an external force, what it wants is to increase the potential energy of the object. And so we have to inject energy to increase the potential energy. While here, the work done by the electric force is the natural motion of the object, so it's losing potential energy. And here we have then a minus sign when we want to compute the work. Very well, so all this is to remind us. Now the problem is very simple. What we have to do is the work is going to be equal to minus, it's a proton, so the charge of the proton was 1.602 10 to minus 19 coulombs. The change in potential, well, they gave us the values, right? So we need to use, this is going to be the initial, this is going to be the final. So the final is minus 55, the initial is 125. And that's it. We will get then this number in joules. So the value here is equal to 4.2, no, just a second. The value here is 2.88 10 to minus 17 joules. So this is the answer in joule. They also want us to write it in EV, electron volts, and it's just a matter of converting, changing the units. Remember that EV is equal to the energy that one electron has. So this is the charge of the electron when it's in a potential difference of just 1 volt. So this gives us the conversion. This will give us a number 1.602 10 to minus 19 joules. So this is the conversion between electron volts and joules.